Welcome back to Csis 248 Operating System Programming. This is the fourth in a series of lectures or lecture sets on C programming. Okay, so this is the fourth part of C, the first video. In this video, we'll start looking at I/O and look at how flags work, and it's something that you want to try to understand, even though it requires some understanding of binary representation, which is something that we don't really get into until a junior level course on computer organization. It's good to know about this. It's good to know about how this works. If some of these things are not completely clear, it's not a big deal. It's not something that I'll quiz you on, but it's something that you might want to try to understand a little better. We look at more expressions, we look at how to detect errors, and specifically look at error number, ERRNO, which is a way of finding out errors in system calls. And we'll be looking at how to print out error messages. Then we'll look at arrays, pointers, and strings. So this will probably be about 6 or 7 videos. I haven't set them all up yet. But over the next few videos, we will cover all of these things. String library functions is very important. And then the Linux memory layout shows you how Linux carves up its memory for each process. And so it'll show you where the stack is, where the heap is, stuff like that. Okay, so we ended up in the last video looking at the two ways to pass parameters in C functions. Actually, strictly speaking, there's only pass by value. But the thing is, in C we can pass pointers by value, and so it's sort of like pass by reference. So only C++ really has, of these three languages, Java, C, and C++, only C++ really has pass by reference. But in C, unlike Java, you can pass pointers, and so therefore we can say that when you pass a pointer by value, it's sort of like passing by a reference. So strictly speaking, only C++ has pass by reference. Okay, so how do you do that? How do you pass by, quote unquote, pass by reference? Strictly speaking, if you look at this, you know that y is just a pointer to a double. And so wherever this is called from, let's say we have a main function where we call this function, we can pass the address of some double precision number. And so strictly speaking, we're just passing a pointer. Of course, Java doesn't have this. Java doesn't have this ampersand operator. And so you cannot do this in Java. And Java does have pass by value, which is actually all this is. It's just that in C you can get the address of anything you want and pass that to a function. And so that ends up acting like a pass by reference. Okay, so the upshot of this is that if you pass in the address of anything, let's say this double precision number, F, and then you put it into here, what you can do is, well, this should say star y equals 10.5. So this is a typo here. It should say star y. And so what this would do is, if you had star y is equal to 10.5, you would be assigning 10.5 to the memory location pointed to by y. So strictly, this might actually compile, but it shouldn't. And what I meant to do was have a star y. Okay, so the idea is that normally when you pass in a double precision number, you can change it inside the function, but those changes are not reflected when you return from the function. But if you pass in a pointer, you're changing the actual location of f. And so in this situation where you have a pointer passed by value, it's sort of like saying whatever you pass in here, in this case the address of f, you can change f, and therefore when you execute these two lines of code, that is assuming that you have a star y here, it's a typo, f will now be 10.5. So try this out. Very simple function called from main. Okay, so let's move on to low-level file I/O. So low-level file I/O allows you to deal with binary files, allows you to deal with files without looking at exactly what they contain, and this can be a lot faster. So it's usually why you would go down to this low-level I/O techniques for files. Also, you can do these if you might hear this expression a lot in Unix and in Linux in general. Everything is a file. So a network connection is a file. So if you wanted to have a raw network connection where you just get input and you store it, one way to deal with those network connections would be to use low-level file I/O. And so we won't do any of that this semester, but those are the kinds of things that you want to be able to do. So you can use low-level file I/O not just files, but a whole range of things, network connections, other things too. Okay, so let's take a quick look at this. We have two calls, open and close. Open allows you to, for this case, we will just restrict ourselves to files. So we have a file name, and then we have some flags. And this is where we need to understand something about binary representations of numbers, because although these are ints, what we're really setting are binary values inside each of these ints. So there's a couple of different variants of open. There's an open with multiple modes. There's a create, to create a file. But the basic idea is these allow you to open a file. Oops. And there's just one close close function, which takes as parameter the handle that was returned by each one of these calls. So each one of these open or create functions return an int. That's the file handle. And that's when you're done with the file, you specify that file handle, you save it, and you call close with that file handle, and it'll return an int. -1 would mean that close failed. Anything other than that, I think, is means that close worked. So here's a simple example. We use open, and we are opening up a named file using read-only mode. And so after that, you can read any number of things using this file handle. So the file handle, in this case we called it file, goes into the read call. And the other parameters of read are an area of memory and how many bytes to read. So with low-level I/O, low-level file I/O, we read chunks of bytes. Okay, so to be safe, you probably want to put in an if statement to check if what open returned, that is the file handle, is actually 0 or greater. It should be greater than 0. And so if the file handle, whatever it is less than 0, it means that the open did not work and you should quit. So to be safe, you should do a check, but just assuming that it's going to work. So for example, if this file does not exist, sure, you'll get, if you open it read-only, yeah, you'll get a negative number for a file handle, and so you'll have to handle that error. So once you're done reading in whatever you want to read in, you can close the file. So remember, the argument to close is the file handle returned by open. So let me just go back one. Remember, you can use any one of these open or this create. They're basically all opening a file, but there's different options. Okay, so this simple example, take a look at it. You can pause the video, but all it does is read 10 bytes of 10 bytes from this file, this specific file, test.in in the parent directory, and then puts it out to standard out using putchar, all 10 bytes, and then it destroys this memory that was allocated using malloc here. So here's the malloc to allocate those 10 bytes of space. Here's the matching free. Make sure that we don't have a memory leak. Okay, so besides open and close, what can you do? You can read, you can write. In the previous example, we opened a file in read-only mode, and so all we did was read. But you can also write. So to write, it's just a sort of the converse of reading. For reading, you specify the file handle and then a pointer, and it doesn't matter to what. So that's what the void star means. Remember that void star means that it's a pointer to anything. It can be a pointer to an int, pointer to a car, anything at all. And then you say how many bytes you want to read. So although this is typed as size underscore t, almost always size underscore t is either an int or an unsigned int. That is unsigned meaning 0 or greater than 0. Usually a 32-bit quantity. It's not obvious from here, but it's usually what it is. Okay, so the write, if you compare with the read, also has a file handle, also has a pointer to an area of memory, and also has a count, which is limited usually to the size of an int usually. And all it does is it goes to this memory location and reads count number of bytes, and that's implicit that this count refers to the number of bytes that you're going to read. I'm sorry, in this case you're going to take from memory and write into this file. Okay, so the return value of each one of these, if it's not equal to whatever you passed in as input for count in either case, then the read or the write did not completely work. If the read did not work, it was probably because there's not enough bytes to read. For the write, it could be that maybe you ran out of space or something, but that's unlikely to happen. So here is a slightly bigger example. You set up in the first part of this program, you set up a chunk of memory from the heap using malloc, and you put the letter D into all 12 spots of this memory chunk. Remember, this is not a string. This is, even though in this case it looks like car star mem, reasonable guess. It's reasonable to assume that it's a string. In this case, it's not a string because it's not null terminated. And so we have a raw array of 12 bytes, which we set to all D's, and we print it out using a putchar function, followed by a new line. We open a test.rw file for reading and writing. We write those 12 D's into this file using the low-level write function. Then we set the whole array of 12 bytes to all A's, and then you read that back in, what you wrote to the file, you read it back in, all 12 bytes, close it, and you print it out. So if everything worked, it should print out all D's, and then it should set it all to A, and then it should put all D's again, if everything worked. So try this out. This is a simple example, and I'll talk about what the flags mean in the next video.